All right, we're in Unit 8, Acids and Bases. I believe we're on question 61. Let's get to the problem. So on question 61, you have this equilibrium reaction. H2 plus I2 yields 2HI. Which of the following changes to the equilibrium system represented above will increase the quantity of HI to the equilibrium mixture? So this is not really acid bases, but this question I stuck in here. That's okay. Let's see. This heat is positive, so it's endothermic, so heat is a reactant. Okay, so here is our, let's just make that nice. Here is our equilibrium seesaw. I know it looks kind of crazy, but all right. We'll increase the quantity of HI in the equilibrium mixture. If we add H2, we added reactant, it goes this way. If we increase temperature, heat is a reactant, so it'll go this way. If we decrease the pressure, nothing will happen because they both have 2 moles here, 2 moles here. I'm looking at the coefficients, 1, 1, and 2, okay? So if your equilibrium seesaw is light on the right side, it's going to create more of that right side. Right? Both of these are going to create more of the right side. They're both going to create more HI, which is what we're trying to ask. Who's going to increase it? So the answer is 1 and 2. The answer is C. All right, this one, wow, what a question. Holy moly. You're looking at these structures. If you notice, they're identical, except for this one has an extra H, this one has an extra I, this one has an extra BR. And to be honest, I didn't know how to do this question. I used process of elimination to get me through it, though. I said to myself, all right, you have these structures. You have this base, table provides the chemical structures for these weak bases and the ionization constants, KB. Based on the data, which of the following provides the best reason for the trend in the base strengths? So I was looking at the trend of the base strengths. I was thinking to myself, okay, he disassociates the most, a little bit less, a lot less. And I'm thinking to myself, wait, is this table right? Now, H is small, but I and bromine seem flipped because bromine is above iodine on the periodic table, so that could be it. So I looked up, I just looked at the answers. It said the number of hydrogen atoms. Well, a number of hydrogen atoms are the same in number 2 and 3. So what? Like, that doesn't make any sense, okay? Number of resonance structures. Well, again, it's the same in number 2 and 3. Like, they both have the same resonance structures, right? Like, this BR could be over here, this BR could be over here, this I could be over here, this I could be over here. So these both have 2 resonance structures. This has 2 resonance structures. This has no resonance structures. So anyways, but the point was that 2 and 3 were similar on both these facets. So it couldn't have been 1 and 2 because if they're the same on 2 and 3, then you can't differentiate. Okay, the different electronegativities H, I, and Br. I was like, I don't know the electronegativities H, I, and Br. Like, the problem was I didn't know what H was. Now I knew that bromine had more electronegativity than iodine, but I didn't know what H was. So, okay. Then again, it said the different molar masses. Well, molar masses increase this way. Like, H would be the smallest molar mass, then it would be Br, and then it would be I. So I was like, wait, these numbers are flipped. So it couldn't be D. D didn't make any sense. So I was like, you know what, it has to be C. I looked it up later, and I saw that the H was a 2.2, the I was a 2.6, and the BR was a 2.96. So that makes sense. However, how the heck are you supposed to know that? I don't memorize all my electronegativities. I didn't like this question for that reason, so I hope nothing like this shows up on the AP exam unless you're good at memorizing all your electronegativities. I'm not. All right. I thought this one kind of easy. I was looking at this, you know, here is your alkane, here's your alcohol. This looks like a, what do you call that? An ester. No, not an ester. An ether. This looks like a acetic acid. Is it acetic acid? No. It's a carboxylic acid. And then this looks like an amide. Okay, so I was just looking at these. Now that's some organic chem functional groups. You don't really have to know that for the AP exam, but you just pick up some stuff over the years. All right, number 63, dissolves in water to form an acidic solution. So I said, oh, well, right here is my acid, D. It was a simple enough question. Even if you didn't know all those different types of functional groups, you know that that's an acid. So 63 is correct. Okay, number 64. Okay, this one caused me problems. Okay, because I didn't know certain things and I was struggling with it. All right, let me show you what I'm seeing here. I saw container 1 having the most disassociation, right? It had the most disassociation because it formed, no. It had the second, this was second in dissociation. This was first in dissociation, and this was third in dissociation, right? Because look, this number 3 is like producing tons of this H plus. This is producing 3 of them. This is producing 1 of them. So the dissociation goes container 3, then container 2, and then container 1. And then I saw that these, okay, I'm thinking electronegativity. The electronegativity increases as you go up a periodic table. So this is the highest electronegativity. This is the lowest. And Br is in the middle. So I had to kind of try to remember, okay, what does electronegativity do in terms of dissociation? Well, the higher your electronegativity is, the high electronegativity means high polar. Like you disassociate easier in polar solutions. So this guy is the highest polarity. He disassociates the most. So I realized at that point, oh, I can label these. HClO is number 3 because it dissociates the most. HBRO is number 1, and HIO was number 2. So I was like saying, so I looked, the correct answer, HIO. So remember, the higher your electronegativity is, the more polar you are. The more polar you are, the easier you disassociate. All right, number 65. All right, this is a little bit more of a straightforward question. Been a while since we had a straightforward one, so let's do it. All right, your KB value with your base is always equal to your x squared over your, your xb or whatever. So your KB is 4 times 10 to the negative 4. You have x squared here, and over here you have 0.01. This means 4 times 10 to the negative 6 is equal to x squared. If we square root both sides here and here, you get x is equal to 2 times 10 to the negative 3. Okay. Now, I don't know what the negative log of 2 times 10 to the negative 3 is, okay? But let me show you a little trick, okay? So if I had 10 times 10 to the negative 3, and I had 1 times 10 to the negative 3, this 2 times 10 to the negative 3 is somewhere in between those two numbers, right? Well, okay, look, this top one, I'm going to change it. I'm going to make it 1.0 times 10 to the negative 2, right? So 2 times 10 to the negative 3 is somewhere between 10 to the negative 2 and 10 to the negative 3. It's somewhere in between there. If I took the negative log of all these things, if I took the negative log of the top one, the negative log would be 2. The negative log here would be 3. That means the negative log of something like this is in between 2 and 3. I don't know what it is. Let's just say, I don't know. Let's just make it easy. It's 2.5. Okay, let's just say it's in between. Again, this is a non-calculator section. So if this is, if I took the negative log of this amount, which is, this was KB, so my POH would be 2.5. And if you remember, pH plus POH is equal to 14. So if my POH is 2.5, then my pH is like 11.5. Right? The answer? Yeah. It's in between 11 and 12. We don't know. See, even then, even the AP exam is not asking for like a specific number, like 11.32159. It's not doing that. It's saying, oh, what's like it's 11 and change. Okay. Okay, which of the following is a weak acid in aqueous solution? Look, I think I mentioned this before. I just tell my students to remember Brickle, No, So, Clo. Okay, these are your strong acids. Everything else is weak, so don't really care about it. Now, HCl, that is, sorry, I shouldn't check that off. It's strong. HClO4, that's strong. I know, you guys are saying, well, you wrote HClO3. Chlorate and perchlorate are both strong. Nitric is strong. Sulfuric is strong. This is your weak. The correct answer is H2S. All right. Let's get to number 67. All right, the graph below shows the titration curve that results when 100 milliliters of 0.25 acetic acid is titrated with 0.1 mole of NaOH. Okay, so you have a weak acid strong base situation here. Okay, all right. Which of the following indicators is best choice for this titration? It's showing the color change. Well, you know what? You want it to change at the equivalence point. That's where you want it. And you know what? I see the equivalence point somewhere between 8 and 10. So the answer would be D, phenolphthalein. That's actually pretty straightforward, okay? What you choose your indicator based on when you get past your equivalence point, which makes this kind of so simple. You just need to know how to use an indicator. That's it. 68. What part of the curve corresponds to the optimum buffer action of the acetate and the acetic acid ion pair? Look, where's the buffer? The buffer always occurs here. This is the buffer region, so the answer would be V. Point V. Henderson-Hasselbalch. Okay, 69. Which of the following accounts for the observation of the pH of pure water? Oh, is 6.8 at 36. Okay, now this means for the if the pH is 6.8, that means the H plus concentration was equal to 10 to the negative 6.8. Now water, where did these H pluses come from? Well, if you think about it, it was H2O, you know, that formed the OH minus and formed the H plus, right? Like these things disassociated. So if you had 10 to the negative 6.8 H pluses, you had 10 to the negative 6.8 OH minuses as well. Those are equal portions. So you know what? When you do your KW here, right? If this is 6.8 and this is 6.8, my pH and my POH, right? This is going to be 10 to the 13.6. Like it's gonna be less than we're used to. We're used to it. Oh, sorry, I should say negative. We're used to water having a KW of 10 to the negative 14. But in this case, when you increase temperature, your KW at 37 is like that number changes from 14 to 13.6, because this is our KW at 25, right? All right, the correct answer here is B. At 37 degrees Celsius, the ionization constant for water, KW, is larger. And I know, right now you're going, no, that's not larger, that's 13.6. No, it's negative 13.6. Negative 13.6 is larger than negative 14. Tricky, tricky, tricky. Okay. All right, number 70. When a strong acid is titrated with a strong base using phenolphthalein as an indicator, they just gave you that phenolphthalein question. The color changes abruptly at the endpoint. The titration can be switched back and forth by the addition of one drop of acid or base. The reason of the abruptness for this color change is that, the answer is A. A large change in the pH occurs near the end of the titration point. How would you know that? Because look, near the end of the titration point, now think about this. It's like this. This is where it's abruptly changing from base to acid, base to acid, base to acid. Like one drop is just screwing this thing up. You want the titration point to be somewhere around here. Okay, so the correct answer is A. All right, number 71. When 200 milliliters of 2.0 NaOH is added to 500 milliliters of 1.0 molar HCl, the pH resulting in the mixture is, okay. I thought this one was, okay, there's a trick here to do this because you don't have a log. Okay, now you have 0.2 times 2, right, of your NaOH, so that you have 0.4 OH minus. Then you have 0.5 times 1, which is 0.5 H plus. So what I realize is I have over 0.1 H plus. Like these 4 OH minuses are going to consume 0.4 of these to neutralize the water, and then you'll have leftover, or I should say, should we say excess? Excess is 0.1 moles of H plus. Now, this is in, now if you add these volumes, your molarity, if you have 0.1 mole of H plus over 0.700 liters of of solution, then you have a 1/7. And I didn't, can I do the negative log of 1/7? I mean, I'm not that good. Negative log of 1/7, I don't know what that is, but let me show you how I did it. I fudged the math a little bit, and this is a really slick technique. All right, so I did, here, let me show you. If you do the negative log of 1 and I do the negative log of 1/10 or 0.1, right? The negative log of 1 is what? 0. The negative log of 1/10 is 1. So this is somewhere between 0 and 1. So the answer is A. So a lot of times, like this one, I don't know. I still don't know. I never put it in the calculator what the negative log of 1/7 is. Instead of trying to find out what the negative log of 1/7 is, you just kind of got to use logic here. And it's really important that you be able to manipulate a logarithm pretty fluidly. All right, number 72. Here we go. What is the pH? Okay, so if I want to find pH, I have to find my H plus concentration, right? So let's see. What is the pH of that? So my Ka is equal to my concentration of my H plus times my A minus over my HA. Okay, so my Ka is 4 times 10 to the negative 10 is equal to x squared over 1.0 times 10 to the negative 2. Then that means my x squared is equal to 4 times 10 to the negative 12. And all I'm going to do is I'm going to square root both sides. And when I square root both sides, this becomes 2 times 10 to the negative 6. Yeah? Now, again, I don't know how to do the negative log of that. Okay? But I do know that this is between 1 times 10 to the negative 6 and 1 times 10 to the negative 5, okay? It's somewhere in between those numbers. What's the negative log of this? 5. Of this? 6. So this one in the middle is going to be, I don't know, 5.5. It's going to be somewhere in the middle of that thing. So when I look for the answer on number 72, I decide that it's going to be D, between 4 and 7. Because it's going to be like 5.5-ish again. Okay, so manipulating those numbers again. Now, there's actually another way to think about this. You know that this is a weak acid. No, I guess that's you're kind of stuck there. All right, 73. What is the H plus concentration of 0.05 molar HCN? The Ka is this, so let's go ahead and do this. Again, your Ka is going to be equal to your H plus times your Cn minus over your HCN. Your Ka is 5.0 times 10 to the negative 10 is equal to x squared over 0.05. You know, I changed that 0.05 to change it. I made it 5 times 10 to the negative 2. That way, when I multiplied them together, I got 25 times 10 to the negative 12. Why did I do that? Because I knew I was about to square root that number, and I really wanted to get a 25 there. All right. I'm going to square root this. I'm going to square root this. This becomes 5 times 10 to the negative 6. So the answer, D. That is the H plus concentration. Number 74. Water, acid, base. Okay. The value of Kw at equilibrium shown is 1.9 times 10 to the negative 15. The pKw is 14.73. Based on this information, which of the following is correct for pure water at this temperature? Okay. So remember, your Kw is equal to the concentration of H plus times the concentration of OH minus. Now, that doesn't happen at it's 1.0 times 10 to the negative 14 only at 25 degrees Celsius, but we're not at 25 degrees Celsius. So what we're saying is that the Kw at this temperature is 1.9 times 10 to the negative 15, which means that is x squared, because the H plus and the OH minus come from the same source. So those values will be the same. They will both be x. Now I got to square root this sucker. And I don't know about you, but I don't know what the square root of that number is. But you know what? I looked at my possible answer choices, and I didn't need to know. That is what my H3O plus is. That is what my OH minus is. They're both the same. The answer is A. So when the math is like really scary, you know, it's kind of like they kind of just tell you, or they kind of give you answer solutions that are not too rough to handle. 75. You have acetic acid again. I mean, man, this if you can't tell, this test is full of acetic acid. They just use this acid so much because it's just the kind of staple weak acid. Okay, equilibrium for the acid ionization concentration of acetic acid is represented by the equation above. A student wants to prepare a buffer of pH of 4.76 by combining 25 milliliters of 0.3 acetic acid with 75 milliliters of 0.1 acetate. If you do the quick math right there, you realize that those are exactly equal, right? And why is that important? Because this is your HA, and here's your A minus, right? Which is we have a really good buffer. While preparing the buffer, the student incorrectly measures the volume of Na sodium acetate, so that the actual volume is 76. So we had, okay, so what happened? We were setting up our pH is equal to pKa plus the log of A minus over HA. Now, what did the student accidentally do? He used more A minus than HA, right? So if he uses more A minus than HA, that's good. It allows for the buffer, right? If you remember, right, we talked about buffers, and we said that this HA and this A minus, like this is when you load up on that HA and you load up on that A minus. But you know what we did? We loaded up on A minus even more. We made there more A minus. So if we have more acetates, just the A minus, then our capacity is higher. Like our ability to endure the addition of an acid or a base, we have more ability to do that. So the correct answer, and without reading every answer solution, is D. The buffer solution will have a slightly higher capacity for the addition of acids than for the addition of bases, because the amount of acetate added was higher than the amount of the acetic acid added. That is correct. All right, 76. Oh, this is a good question. I can see where students are going to make a weird, like a very simple mistake here. All right, a 40 milliliter sample of the weak base that was titrated with 1 molar HCl, so weak acid, strong base, or no, weak base, strong acid. Based on the resulting titration curve shown above, which of the following pairs provides the best estimates for the pKb and the Kb? Okay. See, here's the thing. We're trying to find pKb and Kb, but we have pH. Okay? Now, I can notice something. Here is my equivalence point, which happened at 40. So that means my halfway equivalence point happened at 20. And my halfway equivalence point happened, that looks kind of, yeah, does it kind of look like 11 there? Sorry, I missed a little bit. Let me raise that up. Okay? It's like 11, right? So my pH is 11. That means my POH is equal to what? 3. that means my PKB is like 3, and my KB is equal to 10 to the negative 3, right? Like, so, like, just you stay on track with these numbers and you'll just be fine. Like, I could definitely see somebody actually picking C for this, getting 11, and using these numbers. But this is PKB and KB, but we're dealing, this is actually a pKa because it's a pH, right? Like 11 is a pKa, not a pKb. Okay, you got to switch that over. All right, number 77. Okay, again, weak base, strong acid. The reaction of weak base and HCl represented in the equation above. The graph shows the titration curve for 25 milliliters of aqueous solution of B titrated with 0.1 molar HCl. All right. So this is the information that you need to find right there, because that's where the M1V1 is equal to the M2V2. So you have 50 milliliters times 0.1, right? 50 milliliters times 0.1 is equal to 25 liters times what? And if you can't see, that's clearly double, right? If this thing is being halved, then this thing is being doubled. The answer is A. That's a nice math question right there to make it simple. Okay, this one is something that I don't know if I've ever shown my class. This is something that, this is a diproduct acid. So there's an equivalence point here, there's an equivalence point here. Now, this is when you had the H3N plus and the CH2COOH, okay? Like, this is when you had this was, but then when you got to this, and I'll kind of color coordinate them so you can see it. You have the H3N plus, but then you have CH2COO minus, right? So what happened? It lost an H plus, right? And that's true of that's true of here too. But then you had a second reaction that occurred. You had this reaction that went to here, and that's going to line up over here. This is when you have H2NCH2COO minus. I honestly think that they meant to divide those up, but they actually splinted them together. But I don't care. Okay, point is, based on the data, which of the following species has the highest concentration in aqueous solution of glycine with a pH of 7? So I'm trying to see, where's pH of 7? Oh, there's 7, right? So who is the thing that's most in concentration? It would be this group right here, because it's in between those two equivalence points, right? It's in between, like 7 is hitting right there in the graph where I highlighted in red. So the correct answer, B. 79. Okay, we have these different Kas. The table above shows Kas for 4 weak acids. Which of the following is a pair of chemical species when combined in equal molar results would result in a buffer with a pH close to 7.5? Look, who's the closest to 7.5? Whose exponent is closest to 705? That would be it. You would have to be dealing with something that is near 7.5. The correct answer is C. It's really that simple. Look for the pH, make it a H plus, right? So, like your H plus, concentration of your H plus is equal to 10 to the negative 7.5, and I don't know what negative 7.5 is, but it's closest to that one out of everything that's on that list. 80. The pH of a solution prepared by 10 milliliters of 0.002 molar KOH to 10 milliliters distilled water is closest to. Now, this one was not that bad, but if you doubled, look, we added 10 milliliters to already 10 milliliters. So what did we do? We doubled the volume, yes? So what would that happen to the molarity? Then that means the molarity, right, will half, right? It's inversely proportional. So it'll be 0.001 molar KOH. So now this is KOH. So if I have this as my concentration of OH minus, if I wanted to find my POH, I would take the negative log of this is 1 times 10 to the negative 3. So the pOH is 3. So what's your pH? pH is 14 minus 3. That is 11. The correct answer is B.